Hello everyone, we are back by popular demand. For this video we'll be going over example 12. Okay, so we have been given this RISC-V instruction set, and we want to make a pipelined version, and in this pipelined version we can't access, there's going to be a structural hazard because we can't access the memory for two different instructions. So that's the key point here. I'm just going to read it from the slide itself. Suppose we modify the pipeline so that it has only one memory that handles both instructions and data. So that's the key point here that I was trying to emphasize, is that there's only one memory. So for example, instruction fetch, when we're fetching instructions, we are fetching instructions from the memory, and the address in the memory is the PC counter itself, and then we're going to fetch whatever instruction is at that address. In addition, when we are storing words or loading words, that also uses the memory, right? So because of that, we have to pay attention while drawing our diagram. Okay, so let's begin here. So we'll start with the store word. And honestly, we don't have any data hazards because like all the registers that are used are not used. Like here we have it written over, but it's not really relevant because the computation for the subtract will be done before the write back happens for the add. Okay, so there's no real data hazards here, just structural hazards. So we're going to start with our store word. We're going to start with instruction fetch, and then after instruction fetch there's instruction decode. Okay, so this instruction fetch would have fetched it from our singular memory unit. Okay, then we go execute, which happens in the ALU. Okay, going forward, we're going back to use the mem, but it's okay. It's at two different clock cycles, so we're all good. I'll just use me. And finally, we are going to write it back. There we go. Now load word. Load word, instruction fetch. Okay, so we'll go ahead and we just simply check instruction fetch, everything above it. Well, the only thing above it is instruction decode, and instruction decode does not use the memory, so we will continue on our merry way. Instruction decode, execute, mem. So again, with our memory, we go up, and notice that write back does not use the memory, so we are a-okay to continue. Then we write back. Okay, now we have subtract. So we're gonna instruction fetch. Again, we're gonna go up and make sure that it does not overlap any memory usage, and we're fine. So we can go ahead and write instruction decode, execute, memory. Again, with this memory, we only have write back, so write back does not use the memory. And we're going to conclude this instruction with the write back. Now, what's next? The branch equals. So instruction fetch is what would happen first. But again, with our instruction fetch, we're going all the way up. So notice here, we can't put the instruction fetch here. Why? Because the store word is using the memory at this very moment. So we only have one memory unit, so we can't be essentially fetching an instruction while trying to store some data in our single memory. So there we're gonna insert a stall. Okay, now let's try again. Instruction fetch. Okay, so we have the instruction fetch, and let's go. Here's a memory, and that memory corresponds to a load word, and we're trying to load two pieces of data simultaneously, which is not okay for this hardware that we have, or the hardware that we're given in this instruction. So again, we're going to install, or again, we are going to insert a stall, or install a stall. So let's try again. Instruction fetch. Okay, so we're going to take our instruction fetch, we'll go up. We notice that there's a memory here, but that memory corresponds to sub or subtract. And subtract, in fact, does not use the memory, right? For example, we can go back up to this diagram right here. Okay, so here in this diagram, notice how if we subtract something in the ALU, it can bypass this data memory. So it doesn't have to go through the memory. And because of that, we are allowed to instruction fetch for this at this clock cycle, okay? So now we can instruction fetch, instruction decode, execute, memory. So I'll just write the exclamation mark here because branch equals does not use the memory, and then write back. All right, great. Now what's next? We have add and subtract. Add, instruction fetch, we go up again. If we go up again, everything's fine, so we'll be okay. So then we can instruction decode, execute, mem, we don't use the memory here, so, and write back. And finally we have subtract, and again, subtract doesn't use, or subtract, it does use it, but only for the instruction fetch. And we go instruction fetch and we go up, and notice everything is fine. So instruction decode, execute, memory, write the exclamation mark because we won't use it, and write back. Okay, so that is what is happening for this. Okay, so what does part B ask? In general, is it possible to reduce the number of stalls and nopes resulting from structural hazard by reordering code? No. The reason for this is that every single time, every single instruction has an instruction fetch, and every single instruction since it has an instruction fetch, it will always at some point in time be required to go to the memory. And in addition, if it's during the time that another instruction is using the memory, then it just can't happen. So yeah. What does the answer say? It says reordering code won't help. Every instruction must be fetched. Yeah, basically what I said. Thus, every data access causes a stall. Reordering code will just change the pair of instructions that are in conflict. I'm pretty sure that was a little bit more clear in what version of what I said. And finally, part C, must the structural hazard be handled in hardware? We have seen that data hazards can be eliminated by adding no-ops to the code. Can you do the same with a structural hazard? If so, explain how. If not, explain why not. So, structural hazards, they are flaws, not necessarily flaws, but they are caused by two instructions trying to use the same component. So for example, in our case, let's go back to this flow chart. So in our case, we had a singular memory, so that memory being like holding both the instruction memory and the data memory. So because it was one unified memory, whenever we tried to fetch instructions, we had to use it, and whenever we stored or load instructions or stored or load data, we also used the memory. So because of that, it's a structural thing. Inserting stalls will not will not solve our issue. because it will only just prolong the issue. If we wanted to solve the issue, we would have to simply find another way around it or use better hardware. Anyway, that concludes